Hello everyone. Today we are going to look at section 7.2, which is on the law of universal gravitation. And so our learning targets today are to understand applications of gravitational fields and to identify inverse square relationships. Our essential questions: we'd like to know what gravitational mass is and how the gravitational fields of different objects interact. All right, so let's go ahead and start with a little bit of review. Remember when we talked way back in first semester about the force of gravity acting on an object, we called that the weight of the object. And we said that this works as long as you're on the earth, right? And we had a formula, Fg equals mg. And if you remember this lowercase g, this is acceleration due to gravity. So what we're going to talk about today is a different way to look at Fg. Okay? So I just wanted you to kind of have that in the back of your mind that we've already identified this force of gravity once. Now we're going to look at it a slightly different way. So I'm going to tell you a little story. Here we have a guy named Isaac Newton. Now you might be familiar with him. We know all about Newton's three laws. And there's this very apocryphal story about how Isaac Newton was sitting under an apple tree one day, and the apple fell on his head, and he discovered gravity. Well, that's just silly, right? Because nobody discovered gravity. What Isaac Newton did was he realized that the same force, oh, here's my box, the same force that caused the apple to fall to the earth is the force that keeps the moon in orbit. Now, if you think about that, that's pretty amazing, right? The same force that made the apple fall from the tree is the force that keeps the moon in orbit around the earth. Okay, so that's pretty startling. Now, the difference is that we can identify the weight of this apple, right? Fg equals mg, because it's on the earth. We cannot say that we know the weight of this planet or this moon, right? Because it's not on the earth. We can, however, figure out how strong the gravitational force is between the earth and the moon if we know the masses of both objects. All right? So this is what we're going to talk about today, is how do we figure out the force of gravity between two really large objects? Not a small object like an apple that's on the earth, but a really big object like a planet or a moon. Okay? So in this case, the force of gravity depends on the masses of the objects. And again, we're talking about big objects here, okay? So this is called the gravitational mass. Right? The gravitational mass of the objects. And, this might be logical to you, how far apart they are. The distance between them. So, as it probably makes sense to you, the closer two things are, the bigger gravitational force is. The further apart they are, the smaller they are. Now, the interesting thing about this is that every object that has mass actually has gravitational force. So you have gravitational force. You don't have very much because you are not the size of a planet. But you have some gravitational force that pulls things toward you because you have mass. Not very much. Okay, so how do we write this mathematically? Well, the way we write this mathematically is we say Fg, that's the gravitational force, is equal to capital G, I'll explain to you in just a second what that is, the mass of the first thing, the mass of the second thing, over the distance between them squared. Why do we use r for distance? Because again, we're looking at things circling other things, right? The moon goes around the earth goes around the sun goes around the giant black hole at the center of the solar system, that sort of thing. All right, so that's why we use r. Now, what about this g? This is a capital G. It is the universal gravitational constant. And what that means is universal, right? It's the same everywhere. So if you go to Mars, it's the same. If you go to Jupiter, it's the same. If you're sitting out in space, it's the same. If you go to the sun, it's the same. The universal gravitational, so has to do with, the pull of gravity, constant. Ooh, constant. Doesn't change. Okay, the universal gravitational constant. Anytime you were to see a formula that had a g in it that looked like this, it would always be the same value. Now the value is 6.67 times 10 to the negative 11th. That is a very strange number. It's a very small number. If you were to write it out, you would write 0.2, 3, 4, 5, 6, 7, 8, 9, 10, 6, 6, 7. Okay, that is a really, really, really tiny number. So this gravitational constant is a small, 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 small number, okay? Even though we write it in scientific notation. What does this mean? This means the farther apart the objects are, where'd my box go? Oh, there it is. Sorry about that. What does this mean? This means the farther apart the objects are, the smaller the gravitational attraction is, okay? Now, it also, of course, has to do with their mass. So if their mass is really big, that's going to increase the gravitational attraction. But the further apart they are, that's going to decrease it. So you need to think about both those factors. And because the denominator is squared, the value goes down rapidly. So let me show you what I mean. So let's say I have two things, and I want to find the gravitational attraction between these two things, and they are 2 units apart. Well, that means the gravitational attraction is going to be 1/4 as much as if they were 1 unit apart. Okay, let's look at another one. So let's say my two objects are 3 units apart. Well, that means the gravitational attraction is going to go down to 1/9. Let's say these things are 4 units apart. Okay, now what's my fraction going to be? Yes, 1/16. Good for you. So see, even though I'm only moving them 1 unit apart, the attraction between them is going down rapidly because that value is squared. Last one. I mean, obviously it's not the last one, right? It could go on forever, but this is the last example we're going to do. What's the fraction going to be here? Yes, 1/25. Good for you. And so if I were to graph those, it would look like this, right? I would start out with the biggest gravitational attraction I would have, and as this r gets bigger and bigger and bigger, the gravitational attraction is going to get smaller and smaller and smaller, right? And it's going to go down really fast because of the square, that square right there. So don't forget that there's a square here when you're using this formula, okay? All right, so let's go back and take a look. Gravitational mass, right? The amount of mass that's in the system that's causing the gravitational attraction. And how do these fields interact? Everything that has mass has a gravitational attraction. And so the fields get weaker and weaker and weaker as you get further and further from the object, but they're still going to be pulling on each other. Okay? So let's go ahead and do an example problem here so you can see how this works. Now remember that we have to use some really big numbers here because we're looking at planets and moons. All right, so what have we got? We have the mass of the moon, so I'm going to say mm, right, for the moon, 7.3 times 10 to the 22nd kilograms. The mass of the Earth, so me, 5.9 times 10 to the 24th kilograms. If it's been a while since you worked with numbers in scientific notation, remember that a positive exponent means a big number, a negative exponent means a small number. Okay? And when you type this into your calculator, you got to use parentheses. We'll write it that way in a minute. And the distance between the Earth and the Moon is 3.8 times 10 to the 8th meters. That is a long way. And we would like to calculate the force of gravitational attraction between these two things. Now remember, we're not finding the weight, right? We're not finding the weight of the moon. We're finding the force of gravitational attraction between these two objects. All right, so here's my formula. Fg equals capital G, MM, Me over R squared. I'm going to put in all my numbers, except I'm not going to write the G yet. That's going to come at the end. All right, but I am going to put some parentheses around here. So the mass of the moon, 7.3 times 10 to the 22nd, times the mass of the Earth, 5.9 times 10 to the 24th, over 3.8 times 10 to the 8th squared. Don't forget the squared. Don't forget the squared. Don't forget the squared. Don't forget the, yes, the squared. Good for you. All right, so now I'm going to punch this into my calculator. I'm going to get Fg equals G, and when I simplify the numerator, I get, oh, I don't need parentheses anymore, do I? 4.3, times 10 to the 17th. Nope, that's not right, the 47th. Can't read my own handwriting. Over, now I'm going to square the bottom there, so I'm going to get 1.44 times 10 to the 17th. All right, and now I'm going to divide those. And when I divide those, I get G times 2.9 times 10 to the 30th. All right, and now, since G is always the same, I can write it in 6.67 times 10 to the negative 11th times 2.9 times 10 to the 30th. And when I multiply those things together, I get 1.9 times 10 to the 20th. Now, what are we going to label that? We're going to label that newtons because even though it's a different kind of force, it's still a force. So I have 1.9 times 10 to the 20th newtons. That's a pretty big number that's holding the moon in orbit around the Earth, right? The Earth is pulling on the moon that much. The moon is pulling on the Earth that much. All right, so you have one problem about the International Space Station here, okay, that you are going to use the same formula. So let's write it in. Fg equals G, Ma, Mb over R squared. Okay, and then you also have a review problem where you are going to find the weight of this cat. And so now we get to use the formula with acceleration due to gravity because the cat is on the Earth. Okay? So as always, if you have any questions, make sure that you come to the Zoom and ask them or ask when you're in class next time. And if we need to go over these problems, we certainly can. All right? So I will see you in class next time and have a great day.